Things that burn contain potential energy. So I'm going to use this match as my example. This has potential energy. When I strike it, the potential energy becomes heat and light. And so this is called a release of energy. The energy that was stuck inside the molecules of the wood is now set free. That's what it means to release energy. Combustion is a great way to release energy that's been stored inside molecules. Here with the candle, the wax has potential energy, and we're burning the wax here, making heat and light. Very important in the history of humanity. Before there was electricity, candles provided the light. This apple also has potential energy. Sugar molecules in there. Typically you don't light an apple on fire, but when you eat the apple, combustion reactions occur inside your body. In all cases, combustion requires oxygen gas, produces CO2 and H2O. So in today's lesson we'll look at how much energy comes out when you burn this, how much energy comes out when you metabolize an apple. So please find this page now and complete it as I give you video instruction. First question, balance the chemical equation for the combustion of gasoline. Octa means 8, so this is the 8 carbon fuel. Make CO2 and water when you burn it. How many? There are 8 carbons here, so I'm going to put 8 here. 8 CO2 molecules. 16 hydrogens becomes 8 times 2. 16 hydrogens. Hoping you can now use multiplication. If there are 8 CO2 molecules, 8 of these molecules, how many oxygen atoms are there? If we have 8 of these molecules, it's going to be 8 times 2 is 16 oxygen atoms. 2 in each molecule times 8 makes 16. Over here, this is the water molecule. We have 8 of those. There's only 1 oxygen atom in each molecule. Only 1 oxygen. There are 2 hydrogens, but 1 oxygen. So this is just 8 times 1 is 8. Put them together, and what do we got? 24 oxygen atoms. Therefore, this needs to be 12. So that 12 times 2 is 24 oxygen atoms to balance the right side of the equation. Here I'm putting into the Google Doc the 8 here. And if you're saying it doesn't look right, you can do underline and make the color blue, and then it looks perfect. Question 2 talks about burning gasoline, and it releases energy. You saw this with the match. There's potential energy in the match, and when you burn it, the energy comes out. Exothermic. Burning a mole of gasoline releases a lot of joules. So we need to use a different unit of measurement because this number is too big. The term used is kilo. It's abbreviated with the letter K. It means 1,000. Let me show you what it means. Here are examples of kilo in ordinary life. Real estate will often say the price of a house is 300K, 500K, 700K. What does the K mean? 1,000. A $300,000 house can be abbreviated 300K. In some states, that's a nice house, not in California. Here are grams, and you've used grams in the lab. What happens when you get to a big package, 1,000 grams? You call it a kilogram. So this kilogram here is 1,000 grams. Kilo means 1,000, simple. Now here, we can think that this energy, this heat, is a product of the reaction. So it will be useful to go to the actual chemical equation and put in this number, 5,000 kilojoules. Kilojoules. Make it red. Maybe make it bold. So it stands out as important. This reaction, when you burn the gasoline, makes CO2 not useful, makes water a little bit useful, makes 5,000 kilojoules of heat. That's very useful. That's why humans burn gasoline. Now let's solve problem 2. Burning 1 mole of gasoline releases 5,000 kilojoules of energy in the form of heat and light. There it is. That's the fire. How many kilojoules are released when a gallon? This is a gallon of gas here. Get a lot of energy. How much energy? Let's find out. So I'm going to use this data here, 2,800 grams in a gallon of gasoline. And that's going to be my starting point. Remember, you can make the subscript so it looks nice. I'm using control comma to do that. I'm going to convert this to moles. 1 mole of gasoline has a certain mass. You get it by adding up these parts right here. It's been done for you on this page. 1 mole of C8H16, 8 carbons, 16 hydrogens, weighs 112 grams. So here, conversion factor, 112 grams. 1 mole is 112 grams. This is therefore more than 1 mole. Calculator will tell me how many moles. Trusty calculator says 2,800 on the top, 112 on the bottom, so I'm doing division, and I get 25 as the answer. 25 moles is the answer. These grams here cancel. And therefore I'm left with moles. These grams canceled. So here we have the moles, but we're looking to find how many kilojoules are released when these moles of gasoline are burned. So I know I want to get to kilojoules here as a final answer. I can copy this conversion factor. I'm hoping that you will learn how to be more independent. So instead of having everything all set up with the boxes, you'll have some choices to make. But I can just copy this, copy and paste. And I need a conversion factor that takes me from moles to kilojoules. So let me erase these labels which are no longer appropriate and get the right conversion factor. If you understand dimensional analysis, kilojoules has to be on the top. So I'll abbreviate that KJ, K for kilo, J for joules. Moles has to be on the bottom. And I need the numbers. The numbers are here. 1 mole of gasoline, burning it, releases 5,000 kilojoules. You can also see it in the chemical equation, 5,000 kilojoules from 1 mole of gasoline. So I just put those in the right places. 5,000 kilojoules from 1 mole. This is easy to do on the calculator. It's just 25 times 5,000. And that on my calculator is 125,000 kilojoules. Let's make that stand out. Boom. Final answer. Let's put the equal sign in. Okay, so that's problem 2 solved. That's a lot of energy coming from a gallon of gasoline. So now I'm looking at question 3. This is a really interesting thing to think about. Humans don't run on gasoline. Cars do, humans don't. But if a human could run on the energy contained in gasoline, how much would you need? So this will be an interesting thing to ponder. I've got here lasagna, and humans do run on lasagna, but the energy is the same. It's the same. So here I didn't give you a setup of boxes, but we'll steal the boxes from above. We can take the idea that dimensional analysis can solve this problem. It's just a question of how many boxes do we need. Don't know in the beginning. Let's do it one step at a time. First of all, I'm hoping that kilocalories here can be equated to kilojoules. You can see it in the lasagna label down here. And so that's a good place to start. We need 2,000 kilocalories. How many kilojoules is that? So I'm going to steal a couple boxes from here. Got a little extra garbage. Get rid of the extra garbage. So now I'm going to start with 2,000 kilocalories. Can be abbreviated Kcals. And this is not any specific substance, it's just energy. I want to turn it into kilojoules. I'm hoping you know how to do this with a table in Google Sheets, or sorry, Google Docs. Insert a column to the right so I can have my answer in a column. I need to convert Kcals to kilojoules. So I just formatted it so it's consistent with this text here. This is Arial 11 point, now this is 2. What's the conversion factor between kilocalories and kilojoules? So Google can help you with this. Your teacher doesn't always have to tell you. So if I go here and say Kcals to kJs, you can see obviously people do this all the time. Here's the conversion factor. 1 kilocalorie equals 4.184 kilojoules. There's the conversion factor. Let's go back to the doc and say we know the numbers. Question is which one goes where. There we go. Yep. If we go too far, just undo. Kcals has to go on the bottom. Kilocalories has to go on the bottom, so it cancels these kilocalories right here. Boom. And therefore kilojoules has to go on the top. Now we probably forgot the numbers. Let's go back and look at the numbers. 1 kilocalorie, 4.18. I'll leave off the last 4. 4.18 kilojoules. 4.18 kilojoules for 1 kilocalorie. There we go. That'll get me to kilojoules here. It's simple. It's 2,000 times 4.18. 2,000 times 4.18 is 8,360 kilojoules. So there's step 1. I know how many kilojoules a human needs in a day. You can see it's much less than 1 gallon of gasoline. So let's find out how much it is. There's different ways we can do this. We could go to moles. We could go to gallons. Let's go to gallons first, and then we'll use the power of Google to convert that to milliliters. Good idea. Let's try it. All right, so next step, I'm going to do this again. So I have a blank space, and maybe I'll just kind of blank it out there, blank, 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 blank. Not hard to do. 8,000. Ooh, but this can happen to you sometimes where you're saying, why is it so tiny? And it's probably because it's a subscript. So I'm hitting Control equal, and now it got big. All right, 8,360 kJs. Get rid of the strikeout, which is Alt-Shift-5. Then convert this now into gallons. Gallons is a volume, so it could be the answer to the question, but we'll convert it to milliliters at the end. All right, we know it's 125,000 kilojoules, which I'll put on the bottom here. Right arrow, left arrow. Left arrow will do it. 125,000 kilojoules from 1 gallon of gasoline. Galloon! Yay! All right, gallons of gasoline. If it wraps, stretch it out. Yep, now it doesn't wrap. Okay, so this is now a simple calculator problem. 8,360 kilojoules is already on my calculator. 1 on the top, divide by 125,000 on the bottom here. And get a tiny number here, 0.067 gallons of gasoline. So that's true. It's just not really useful saying how big is that? So let's do one more conversion. And let's convert 0.067 gallons. I'm copying and pasting again. Into milliliters. So instead of gallons, we'll have milliliters. I'm hoping you're familiar with that from the lab. And now we just start with where we left off, 0.067 gallons. And here we'll get this from Google. We'll get this from Google. Right arrow allows me to navigate easily. Already know the labels because it's dimensional analysis. Gallons will be on the bottom and milliliters will be on the top. All I need is to know what is the conversion factor between these two. Google will tell me. Gallons to milliliters. ml. Boom. All right, once again, we will round, but 1 gallon is 3,785 milliliters. Back to the document. 3,785 milliliters is 1 gallon. Check, make sure I didn't lie. 3,785, 1 gallon. Okay, so that's going to get us an answer that I made an error here, didn't I? Bad me. Boom! It's 0.067. 0.06, it's 0.067 gallons, not 0.67 gallons. Okay, that's already on my calculator, which makes it easy. 3785 milliliters. 253 milliliters is my answer. That's a nice answer. I'm going to get a picture of what does that look like. So here I did a Google search, image search for 250 milliliter beaker. I like this one. So there it is, about this much gasoline. If your body could metabolize gasoline, this would have enough energy for your whole day. It's about 1 cup. So that's kind of interesting to think about. So if humans could metabolize gasoline, this would be all the energy you need for the day. And instead we have the pleasure, but sometimes the curse of saying, no, we need a lot of different kinds of food in our diet. These are things that give us, as humans, energy. The gasoline, we can't use that energy. Another way of looking at it is to say this much gasoline, a gallon of gasoline, could feed a person for 16 days. So if we could metabolize gasoline, maybe that would solve some of the world's hunger problems. So a tank full of gasoline for your car, maybe 15 gallons. That's enough energy to feed a human for almost a whole year. So think about that. Next time you fill up your car, the energy there could feed a human for a year.